Yeah, so today's whiteboard is going to cover a couple of papers, one of which is called Glean, Structured Extractions from Templatic Documents, and the second of which is called Representation Learning for Information Extraction from Form-like Documents. They both kind of cover the same general area, which is the development and management of a system to extract structured information from these kinds of templatic documents. And they're written by the same authors. The Glean paper describes kind of the broad architecture of the system and kind of how it works. And the second paper discusses a bit more of the internal details of how you might train such a system. And so it kind of makes sense to put them together, and we'll be using kind of figures and diagrams from both of them to kind of get to the point. Also, I did not write these papers. I just read them a few days ago. So if there's anything cool you learned from today's talk, it's because of the authors. And if there's anything that you think is wrong or weird or messed up, it's totally my fault. And I'm going to take the blame for that. Anyway, so the structure of the talk is going to start with an introduction. So kind of just a review of relevant work. Why do we care about extracting structured information from templated documents? The second part is going to discuss the architecture behind the models that the authors propose. And the third is going to discuss design decisions and considerations about managing data and dealing with such a system. So with that, we'll get started. So as an introduction, what is structured information extraction? Why do we care? Form-like documents are super common in today's workplace, but they're not standardized and they're challenging to process and extract information from. So basically, if you look at the examples that there's a bunch of different invoices, different invoice templates that people use, and none of them are standardized in any means. That template at the top left, if you train the vision model to predict the date from the template at the top left, any of the other templates would be out of sample. And it's pretty difficult, even for humans, to understand what kinds of patterns are present and how you might extract the date in a consistent manner. So the non-standardization of these templates makes them challenging to process and extract information from. As an example, different vendors will process these kinds of invoices thousands of times a week, and without much prose, you'll have to kind of rely on patterns and NLP to make some sort of an educated decision about what kinds of fields to extract and where the values might be. So traditionally, this problem has been approached in a few interesting ways. The lack of prose in template documents makes it infeasible to apply approaches based purely on NLP. So one might imagine one way to do this, if the invoices were all paragraphs, would be to extract the text from the invoices and train some sort of a representation learning model. BERT kind of comes to mind, to extract relevant answers for certain questions you might ask about the document. But without a lot of prose, it's hard to use purely natural language-based approaches to solve these problems. So understanding spatial relationships is pretty important. As an example, an intermediate way of doing this is information extraction from web pages, where work in the spaces involved leveraging source markup representations to extract relevant information. Of course, source markup doesn't exist for structured documents like PDFs, so we can't entirely use that kind of a template to extract information. Instead, we'll have to purely use visual and natural language-based cues. And much work has been done to improve parsing abilities for the construction of document graphs. And so given a PDF, there has been a lot of work that has been done to extract relevant text and tables and templates from those kinds of documents. But these methods require large amounts of training data and are tough to generalize to new templates. So it's relatively complicated to use these methods and directly apply them back to extracting fields from documents. So given all of this, the authors of both papers have proposed 3 key observations that lead to the design of their system. And so we're going to go over those observations next. Also, feel free to interrupt if you have any questions or if any of this isn't making sense, if I'm talking too fast, things like that. Always happy to slow down. The talk isn't super technically complicated, but hopefully the key points get across. So the first observation that the authors propose is that each field often corresponds to a well-understood type. And so to clarify vocabulary, fields in this type of context basically refer to things that you'd like to extract from these structured documents. So a field, for example, might be the invoice date in an invoice. And the observation here is stating that each field that you'd like to extract often corresponds to a well-understood type. So for example, the invoice date field has a type of date, obviously. And so the only likely extraction candidates for the invoice date field are text instances that are formatted as dates. The implication of this is that candidate generation can be performed using a library of detectors, for example, regular expressions for common types. So if you'd like to take a look at a PDF document, for example, and look for candidates that might correspond to a particular field, to generate those candidates, what one possible approach might be that is validated by this observation is to look through all the text in the PDF and apply a date-based regex and look for all of the things that match the dates, because these fields often have enough well-understood types that you can simply do that and obtain reasonable candidates. The second observation is that each field instance is usually associated with a key phrase that bears an apparent visual relationship with it. So what this means is that each field instance has in its surrounding context key phrases that relate very strongly to what that field instance might represent. So there might be multiple date instances in any given invoice, maybe the invoice date, maybe the due date, things of that nature. But the one next to the invoice date, or the one that is the invoice date, likely has the word invoice date or dated next to it. So if you go back to the earlier example here, you can see that for the invoice date, there's invoice date, and dated. And those are all key phrases that are near the invoice date. Obviously, they're not on the same line all the time. So in the top left, the date is above the invoice date, but it's still within their surrounding context at the invoice date. So these key phrases are often in the neighborhood of the actual invoice date. They obviously, like we said earlier, may not always occur on the same line, but they're often near in the neighborhood of the field instance. And the implication of this observation is that effective solutions need to combine both spatial information with textual information, because these key phrases are important to provide context for what the field instance right value is. And the last observation is that key phrases for a field are largely drawn from small vocabularies of field-specific variants. And so what this means, and this is actually probably the most important observation, is that while it's hard to generalize to out-of-distribution templates, so if you look at a small subset of invoice templates, and the question is, can we generalize out-of-distribution to different kinds of templates? The answer is almost always no, because it's very hard to know exactly, if we're looking at tables in our train set and we're looking at paragraphs in our test set, how might we understand that? This observation says that the things that do generalize are key phrases for the field. So for example, in the corpus the authors examined, only 7% of the invoice dates had neither date nor dated in their key phrases, and similar patterns were observed for other fields. The implication of this is that the problem of extracting fields accurately is tractable with only a modest amount of training data. That is, you can base a lot of your generalization capabilities on whether you can extract and understand the key phrases for the field, as these generalize a lot more than most other things in documents do. Cool. So these are the three fundamental observations about extracting fields from templatic documents. And the authors then use these three observations to develop their system that is based on candidate generation and representation learning. So the next part of this talk, we'll discuss exactly what this architecture is, how we might extract information with candidate generation and representation learning based approaches, and why that might be exciting as an avenue for generalizing out of distribution into new templates. So, so the general architecture that the authors propose is kind of represented in the second bullet point, and there's a little vocabulary here and a lot of missing pieces that we'll go into right after this slide. But the general pattern that the system follows is, given a document and target schema, again, we'll explain what those two things mean in a little bit. They first generate extraction candidates for each field from the document text using field type information. Basically, what this means is that for each given field, it has an associated type. You extract all the text in the document, and then you look for candidates in that extracted text that have the given type that you care about. Each candidate is then subsequently scored independently, and at most one candidate is assigned to each field. So these scores correspond loosely to how likely it is that these candidates correspond to the fields that we're looking at. And then of course, assignment is performed to assign each candidate to the fields, and that's the final output of the model. So this model isn't similar to a purely vision-based or a purely NLP-based approach. It relies on candidate generation and then scoring of the candidates to produce a final output. So there are four key stages to this architecture. There's ingestion, there's candidate generation, there's scoring, and there's assignment. And these are the four stages that we'll now go into. But before we do that, here's the super exciting and really illuminating figure that was in the paper that kind of describes the overall system. So you start with a document, which they represent as an image, and a target schema, which is at the leftmost side, where the target schema just indicates what kind of fields you want to extract and the types of those fields. You then run OCR in the document to get some sort of a representation of what text is in the document, and you apply candidate generation to the OCR results based on the field types of the target schema. So for example, there might be a candidate generator that is simply a regex that operates over all the OCR text and looks for things that look like dates. And you can see at the right result of the candidate generators that all the things highlighted in blue look like dates. The same thing is true for prices. If there's a dollar sign next to it, or if there's a certain kind of, again, probably done with the regex, you can get a bunch of candidates that represent the price. You can then score these candidates, and the way scoring happens will be discussed a bit later in this presentation, and then assign the candidates. Here, it's simply assigned based on the highest score to get the extraction results. So hopefully that clarifies a bit what the paper does, and we can now go into I guess, each step of the process. So the first step of the process is ingestion and candidate generation. So there are two inputs to the system. There's a document, obviously, and the document is processed with Cloud OCR to extract a hierarchy of text from the document. Each level of the hierarchy is associated with bounding boxes and the 2D Cartesian plane of the document. So it's basically just a bunch of boxes, and there are different levels of boxes, starting from like individual characters to overall words and bigger parts of the document. The second input is a target schema. Users are allowed to define targets of a wide range of types. And so the example here, there's an invoice date, which is type date, a total amount, which has type price. And each type is associated with a predefined candidate generator that is given to the user that matches spans of OCR text. So different types of generators, for example, there are regexes, knowledge graph entity detectors, dictionaries, etc., whatever you can think of. But basically the idea is, given a type, how do you find instances of that type in this OCR text? These generators are crucially designed to be high recall and might give up on precision as a result. Basically, you want to capture every date, because if you miss a date, that's your ceiling for your performance. If your generators are not strong enough, or sorry, not weak enough to capture all different variants of dates, you might never get the right answer. And the whole point of the scoring mechanism then is to improve precision, is to basically allow from that selection of candidates to pick the one that is most likely to be the right candidate. Cool. The next step is candidate scoring. And so the way this works is each field has a bunch of candidates. As you can imagine, at the top right, you can see that the date, all the candidates are in blue, and for the price, all the candidates are in orange. And each field candidate pair is scored to estimate the likelihood that the given candidate is the right extraction value for the field. So this is probably the most interesting technical part of the paper, is how you might score this and how you might create an interesting mechanism that allows for you to associate the right candidate with the right field. And so the scoring system is comprised of two neural networks, which together embed the candidate in the field in the same space using a cosine similarity objective function. And so the way this works is candidates are embedded based on the neighboring text tokens and positions and the candidate position. Crucially, the paper makes a point to not embed the candidate itself. And the reason for this is because if, for example, your training set consists of, using the invoice example, only invoices dated at 2018, you don't want to use the date of the invoice of the candidate, or sorry, the date of the candidate to be an indicative feature, because this might not generalize out of sample to candidates from 2020, for example. And the field is embedded as well. And the way these embeddings work are the text is embedded with a normal text embedder, the position is embedding with a 2D position embedder. Self-attention is applied across all of the neighbors so that the embeddings are not independent of one another. The candidate position is also embedding and concatenated with the embeddings of all the text, the neighborhood text and their positions to get an overall candidate encoding. The field is also embedded and simply dotted with the candidate encoding to get the overall score. So basically the idea behind this scoring model is to embed the candidate embedding, the field embedding in the same space. And obviously it's pretty easy to train such a system. All you really have to do is to get a ground truth sample of positive candidates and negative candidates. And then you can train the model with something as simple as cross entropy, because the score is between 0 and 1 after normalization. So the general idea here is, how might you represent candidates and fields in a space where candidates that are likely to be associated with the field have high dot products with the field or high cosine similarities, and candidates that are far away or distinct from the field have low dot products or low cosine similarities. And that's exactly what the scoring model here does. So the scoring model is trained with human labeled ground truth, and this is provided by either human labelers or a public data set that has ground truth observed. And we'll get to exactly what it means for something to be ground truth, or heuristics for how you might do this a little bit later in the talk as well. So what are the benefits of this approach? Well, high recall candidate generators reduce the search space for the scorer and make the learning problem more tractable. So because we don't have to look at all the text in the document, we only have to look at the text that is extracted by the candidate generators. We don't have to look at the whole search space, and it's easier for us to kind of deal with these kinds of search problems. And separately encoding the candidate in the field produces a field agnostic representation of the candidate, of the neighborhood of the candidate, which is useful because, as in observations 2 and 3, the most indicative factor in determining whether a candidate is associated with a field is its neighborhood. And so embedding that neighborhood is important. And there is some intuition behind why this neighborhood might be ultimately useful in determining if a candidate is the right value for a field. So The figure at right is just a simpler representation of the figure we saw here, the scoring model we saw here, where basically the candidate and field are both embedded, scored based on cosine similarity, and this score is then assigned to each of the candidates. And the assignment process then is super simple. All the scores are in a range 0 to 1, so a single candidate is then chosen for each field based on these scores. An interesting point to note here is that while the highest scoring candidate is always a reasonable choice, arbitrarily complex rules can also be encoded here. For example, if you're extracting the due date for a due date for an invoice and the invoice date, there are certain hard constraints. For example, the due date for an invoice cannot precede the invoice date, and so that might be used to break ties or to better adjudicate what candidates to finally select in the overall outcome. So that kind of concludes the overall representation of the model architecture. Before we go into experimental results, if people have questions or anything, happy to take them. Hopefully this is making some sort of sense so far and it's kind of useful. But yeah, so I'll pause for maybe 10 seconds.
I have one quick question about, field and candidate. I can imagine like candidate is, for example, for data extraction is like, for example, June 25th is one candidate. Or what's the field in this case?
So the field is the thing that you like to extract from the document. So if June 25th is a candidate, the field might be the invoice date, the due date, like something like that.
Okay, so what's the features about this field?
Yeah, that's a good question. I don't think the paper was super clear about this. I think it's as simple as like just an embedding of the field ID. So it's like you might imagine like an index into an embedding, like into like a torch embedder, where you just like have a different embedding for each field, and then you train the embeddings based on the neural scoring model. So there aren't features per se for the field. I think it's more just like an ID that corresponds to some sort of embedding that is learned.
Like a field ID, like you said, a 25, for example, is that comes from the document itself?
I think that it's arbitrary. I think that they just assign fields to, or they have field IDs, and then you just embed the IDs. Yeah, so it's just like a learned embedding based on the scoring model. I don't think there are features for that. The features come from the candidate embedding, as far as I understand it.
Thank you.
Yeah, cool.
One quick question. It seems like, do you need to have the fields basically like you have to have the list of all the fields you'll ever want to extract before you start training your model, or does this try to learn like more general like field and candidate? So like, for example, if I wanted to, extract another field, like the manufacturing date of the product, the document, like would I have to add that new embedding and retrain the whole model from scratch? Or is there like sort of a way of like reusing what I've already trained?
Yeah, I think based on my understanding and based on I think how this is structured, you'd have to retrain because the fields, I think like Karima was pointing to, the fields, as far as I understand it, don't have embeddings based on features. I think it's a learned embedding based on the scoring model. So if you added the manufacturing ID, there's no reason that embedding would correspond to anything. You'd have to relearn the similarity between that and the rest of the candidates for this scoring model to make sense.
Very cool.
Quick question, Manan. I think you mentioned this somewhere, but is the position embedding just like the bounding box information?
Yeah, so I didn't mention that. So that's my bad. The position embedding, I think, is some sort of like in BERT, it's like a sine wave or something. It's like a positional embedding of like the XY coordinates of where the neighbor is.
Got it. So if you were looking at like your neighbors, it would just be like its relative distance in like that two-dimensional space.
Yeah, exactly. It's relative distance to where the candidate is. And there's a figure in the paper that makes this more clear that perhaps I should have included. But basically, they look at the bounding box. They have some sort of delta range around that bounding box that corresponds to potential neighbors. And the positions are the plus or minus X and Y delta from the candidate. They might also be absolute positions, and I'm not confident about that. I'd have to look at the paper again, but it's something like that.
And so like things like adjusting for font size wouldn't be something that's like necessarily captured terribly well.
Yes. Yeah,
like
you're right.
Just a huge text, like, and then like everything just is far away from it. You won't necessarily be able to.
That's a good point.
Neighbor information.
Yeah, I think you'd have to make that explicit in your deltas. Like if you're using bigger font sizes, you probably have to have bigger bounding boxes.
Got it. Cool.
Awesome. Any other questions? I hope this is relatively clear so far. Awesome, exciting. Okay, cool. So the next portion is kind of experimental results. The one slightly unfortunate thing about this paper, I think, is, and this might just be true about the field in general, is that there aren't necessarily obvious comparison or like standardized benchmarks for comparing information extraction on different problems. So the two data sets that this paper used are an invoice data set and a receipt data set. So the invoice data set consists of 14,000 single page documents. They're extracting 7 fields, and all the information is in that table at the right. And the ground truth is human annotated. I don't think they provide this data set to the public, but they ask human labelers to label all possible instances of the amount due, the due date, the invoice date, etc. And the second data set is a receipt data set that consists of 626 receipt images, which is public. And I'm realizing now that obviously none of you can click on the link in this slide. But if you look at the paper, it's very clearly linked in the paper. It's, I think, like footnote 3 in the second paper that I linked. And there are 626 images. There are 234 templates that they correspond to. There are 2 fields to extract the date of the receipt and the total amount. And the ground truth is provided. This is like a public data set that I think is a benchmark, but again, I'm not super well versed in this field, so I'm not sure how general or how much this benchmark is used in other problems. And they compare their model to 2 base. Oh, sorry.
Sorry for interrupting. I'm just, I think the layout LM papers use that as one of their data sets.
Oh, cool. Okay, that's good to know. Yeah, I guess I don't have that much background in this field, but that's good to know. So I guess the receipt data set is a bit more like visible. And yeah, so the baseline, so the 2 baselines they compare it to are a bag of words baseline that uses neighboring tokens, but not the position encodings, and an NLP baseline that does use position encodings, but no fancy attention things, just 3 hidden layers and for embedding. And the results that they observed, you can see for yourself on the table at right. Their model obviously beats the ablations without the fancy attention stuff and without the positional encodings. It's not always super significant how much that the model beats these 2 benchmarks, but certainly it is the case that their model is able to outperform these benchmarks and obtain reasonable AUCs and F1 scores. So the model itself is relatively promising and does indeed perform quite well on unseen templates for invoices and receipts. So one maybe important point to note is that especially for the invoice templates, the invoices are not all standardized. They're not all from the same template. They come from, as we saw earlier in the presentation, templates that look very different from each other. And so this method of candidate generation and extraction is pretty useful and does have promising implications on generalizing out a sample, which I guess at the end of the day is kind of the whole point of why you might want to do such a thing. So that's useful. Other experimental results include an examination of internal representations. And so there's a couple interesting graphs here that are maybe worth examining a little bit closely. So the leftmost graph is a TSNE visualization of positive candidate encodings for the date fields in the target schema for the invoices. And basically what you see here are the candidates that correspond to certain fields are all embedded close together in TSNE space. This is obviously very good. This is exactly what we're looking for. We hope that candidates that all are correct and correspond to fields all have similar embeddings. So that's good. And the graph at right is a visualization of positive and negative candidate encodings for one particular field, which is the invoice date field, as well as the invoice date field embedding. And so what we see here is that the invoice date field embedding is in blue. The positive candidates are in green and the negative are in red. And indeed, we do see that the positive candidates are close to the field embedding and the negative candidates are far away from the field embedding. But they're more scattered. And this is because the loss function minimizes the distance between the field embedding and its positives and maximizes the distance from the negatives. But there's no reason that the negatives have to be close together in space. They're all spread out far apart, but they're far away from the positive embeddings, or they're far away from the field embedding, which is close to the positive embeddings. And that's all we really care about is it the case that the cosine similarity between the field embedding and the positive embeddings is high and higher than that of negative embeddings? And that seems to be the case. So this is a good, I guess, proof of concept that this method and that the scoring function works as intended. Okay, so the final part of this talk deals with some design considerations. So this is mostly from the Glean paper. How might you manage data like this, deal with kind of practical issues for managing such a system? And there's a few, most of these are heuristic points or like points to kind of keep in mind if anyone here wants to design their own system. The first point is that the choice of OCR engine has a super important impact on overall performance. It's up to 6.5% or 6.5 points in the F1 score. So pick a good OCR engine, probably pretty obvious, but I guess maybe less obvious is how important of an impact the OCR engine ended up having on their performance. The second point that is slightly more subtle is when you generate positive and negative examples from the training data, what you might imagine is you should ask your annotators to label all the possible candidate or true candidates that correspond to a field. And so, for example, if the invoice date is listed in the document and at the top and bottom of the documents, label all of them. So that's maybe more of a given. But then the question is, how might you determine if candidates are ground truth true or ground truth false? So there's 2 ways to do this. One way is you look at a candidate that you generate, and you look at the intersection of our union bounding box, the bounding box intersection of our union with the true candidate that a human annotator has labeled. And this is what the paper calls match by position. You can also look at type-specific semantic equality. Basically, what this means is, given a type, so for example, given a monetary amount, you literally evaluate the monetary amount and you compare that to the human annotated monetary amount, and you see if they match. And if they do match, it's a ground truth positive. Otherwise, it's a ground truth negative. So certainly, at the end of the day, you want match by value to be true. No one really cares about the bounding boxes. They care more about extracting particular values from the document. But what the authors of the paper observed is that a practical recipe for doing this that is more sample or more trained data efficient is to instruct human labelers to mark all the instances of a field. Then second, use match by position to generate the training data. So instead of using literal evaluation to generate candidates for the training data, instead use bounding box intersection of reunions, because this ends up generating more training examples, and most of them are true, and it's useful, I think, for generalization capabilities as well. And then use match by value to evaluate the extractions. So all the results that you saw in the table are done with match by value, which is what you expect. So maybe slightly more of a subtle point, but when you generate candidates, use match by position, and then when you evaluate them, use match by value. So that's the point of that. In terms of training data management, there's a few other subtle points here. It turns out that candidate generation and the development of these candidate generating functions are super important and have a very big implication on F1 score deltas. So they had an example, I think, in the paper of allowing or disallowing spaces in one of their regexes for candidate generation. And simply the difference between allowing or disallowing spaces had a 7-point F1 score delta. So again, maybe slightly obvious, like you want your candidate generation functions to have high recall. You want to capture a lot of value in these functions, but slight variations or even mistakes in these functions can result in significant deltas in performance. Another slight note is if no positive candidate for a field has a ground truth for that field. So in the training set, if all your candidates generated, none of them overlap with the true candidate, discarding the training example ends up improving the F1 score by 5.3 points. And they call these like unable to match documents, where including them in the training set just causes more complications and makes the problem fuzzier. So all these are pretty significant F1 score deltas. And the important comparison that the paper makes, I think the overall point of the paper is that all these deltas, training using match by value, retaining unable to match candidates, retaining overlapping candidates, and disallowing spaces in an example candidate generation function, all have significantly higher deltas than using a simple model architecture. So you can always use a simpler architecture and get reasonable performance as long as you're doing the other things right. But if you mess up any of the other things, that deviation in performance far outshines any performance gain you might get from a better model. So modeling is important, but all these smaller considerations, writing better candidate generation functions, things like that, far more important. And that was kind of the point of these ablations, I think, in the Glean paper. And finally, last slide, I hope everyone's still awake. Framing the problem using candidate generation results in more inexpensive models than the traditional models like BERT, GRID, or things of that nature on the corpus of 14,000 invoice documents that the authors were using, with 1.3 million candidates generated using all of their candidate generation functions. Training on a single GPU required 45 minutes. And BERT GRID, which again, haven't read the paper, so I don't know exactly the details behind it, but the first 4 letters are BERT, so you can kind of guess where it's coming from. Extract directly from the document without candidate generation requires 1,090 minutes on a GPU. And the paper says this has similar or worse performance. They don't quantify what this means. And so, it's unclear exactly what the difference in performance is, but certainly the difference in training is pretty significant. And the generation of candidates is intuitive and useful and probably generalizes more out of distribution than BERT GRID does. So there are benefits there. And in terms of inference, the OCR stage dominates inference time. Scoring and candidate generation at inference doesn't require that much time. As you can kind of tell, the model is pretty small. There isn't that much to it. In terms of like, I guess like GPU power required, and assignment stages are negligible. So certainly like the model is relatively fast and it's useful and probably generalizes quite well. And all these modeling decisions are pretty important, far more so than I guess model architecture decisions. And yeah, so that's the final slide. Hopefully that was useful to people. I guess if there's any cool things you learned from this, again, thank the authors. Anything that you think I messed up, sorry about that. But yeah, I hope you all learned something. Thanks.
That was awesome.
And also happy to take any questions. Yeah.
Yeah, I had one question. Could you say a little bit more about where, experts or kind of non-technical users would kind of fit in? I think the authors had mentioned that it was designed for those interaction modes in mind. So we'd be curious to see what your take on that one.
Yeah, absolutely. So there's a couple of places where I think that the candidate generation system does a really good job at using expert kind of like information. The first point is in candidate generation functions. So there's obvious like ways that you can generate candidates for like dates and for prices and things, but perhaps for more subtle candidate generation functions or improving the recall of these functions, kind of capturing more of the text of the OCR spans. It's important to write candidate generation functions that do kind of correspond to large amounts of like what you're looking for in the text. And so experts and humans that might have like better insight into the problem might be able to write better candidate generation functions. So instead of looking at all prices, perhaps prices should all be above a certain value or shouldn't be negative or things like that. And that's kind of, heuristics you can add on to these generation functions to make them better. And the second thing is in the assignment stage, but because this is all done with candidate generation and extraction, when you have candidates and their scores, you can apply heuristics to these scores to select candidates that make the most sense. And so the example that was in the presentation was, if you have an invoice date and a due date, certainly the due date should be after the invoice date. And so the value is, if you have a bunch of candidates and they have similar scores, the scores aren't super useful. You can apply hard heuristics on top of the scores to kind of have a better like overall outcome. So there's that.
Cool, thank you.
Cool, yeah, happy to take any other questions, but yeah, hope that was helpful to people.
Your last slide, I think, does such a great job of summarizing a lot of the things we've learned over the last few months with our work internally, just like recognizing that, yeah, perfect. Like if you can generate candidates for the task and get 100% recall, absolutely the way to go, like for various reasons, just like improving training time, significantly. You having your first bullet and second bullet, and then just recognizing recently, like learning that, hey, like running OCR is a very expensive, time-consuming process.
Yeah.
And this is going to hurt the experience of the user if it's something that they expect to happen online versus batch. And that candidate generation can be really fast and take up a negligible amount of time. So yeah, I think this just really underscores a lot of things we've learned over several drives to quality recently.
Absolutely. Yeah, well, glad to hear it. I think that another super important thing to consider is I think that a lot of the points that this paper is making is that candidate generation allows for generalization out of sample in ways that BERT grid probably doesn't. In the three observations, I think earlier in the talk, it seemed pretty clear that the things that do generalize are the I guess like, man, I forgot what they were called, like the relevant like text surrounding the candidates, and that is the stuff that you embed, and that's the stuff that you can get pretty easily with candidate generation. It's difficult to see how visual representations over the entire document might generalize. And of course, it's easy to see why that requires a lot of performance, downsides. And so candidate generation does seem like a pretty promising way to go forward with this sort of stuff. Yeah.
Yeah, and another +1 to underscore that point, I think what we've seen here, and the way that we build systems is to really emphasize this kind of decomposition, right, of complex systems. I think this is a great example where, hey, one monolithic end-to-end model, could be great and could work in some settings, but having each step, broken out where you can debug and understand the impact of every component individually ends up being a really powerful way to, very, very practically build these sorts of systems. So just another +1 to some of these really opinionated ways that we've been designing these sorts of systems, and something that we'll have to keep in mind as we move forward in more and more complex applications.
Absolutely. Cool. Well, if anyone else has any other points or topics, things to talk about, happy to talk about them. But otherwise, that's the talk.
Awesome. Well, another virtual round of applause for Manan. That was awesome. Thank you for your really great summary, and yeah, thank you for the folks in the audience who joined us, and we'll do this again soon.
Thanks, everyone. See ya.